So 2015, what happened? I'm going to tell you what happened by talking about the source of gravitational waves that we saw. 1.3 billion years ago, in a galaxy far, far away, two black holes circled around and around each other, and you can see them better on the side screens where the resolution is better. The two black holes circled around and around each other. They made these patterns, just like the patterns I showed you before, but now with them going around as more interesting patterns, Einstein rings that are more complex. And as the black holes circled around and around each other, they gradually lost energy to the gravitational waves, and so they spiraled closer and closer together, with gravitational waves getting stronger and stronger as they spiraled together. And those black holes, as they neared each other, they collided and merged in a gigantic cataclysm. The gravitational waves they emitted traveled out of the galaxy in which the black holes lived. They traveled into the great reaches of intergalactic space, across intergalactic space. They arrived at the outer edge of our Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. They traveled for 50,000 years through our galaxy and arrived at Earth on the 14th of September, 2015. 3 days before our first gravitational wave search with what we called our advanced interferometers was scheduled to start. These interferometers that by then had been built, they were very complex, and they had to be tuned in many, many ways. And so the tuning was nearly finished, and this signal came in. And David Reitze, who was Barry Barrios' successor as director at that time, he declared the first search has begun because we saw something. And so the first search was off and running. The signal, when it came in, it went up through, let's go back, it arrived at the down at the Antarctic Peninsula, traveled up through the Earth unscathed. Oh, where am I going? Okay, up through the Earth unscathed, and came out of the Earth at the LIGO gravity wave detector, or interferometer, in Livingston, Louisiana. And 7 milliseconds later, it came up out of the Earth at the LIGO detector in Hanford, Washington. This signal stretched and squeezed the mirrors, pushed them closer together and farther apart at the ends of these long arms. So the laser beams are inside pipes and bouncing back and forth, and the mirrors are at the ends and the corner of these arms. So the mirrors are pushed back and forth by the gravitational waves, and then the light recombined, as Ray Weiss had originally described, and that recombined light then had an intensity that went up and down, and that it was fed into a computer that analyzed the data, and the computer compared the oscillations with the predictions from computer simulations of colliding black holes. The LIGO collaboration, together with something called the Virgo collaboration, which was primarily at the time a French-Italian collaboration, which had also built interferometers of this sort, but their interferometer was not yet working. They participated in our data analysis. And so the two teams together, participating in the data analysis together, took 5 months to analyze the data and become totally convinced that this was really real. There were so many things that could go wrong that it was necessary to go in and study the signal and study the output from many auxiliary output channels. 100,000, there are 100,000 auxiliary output channels that tell you what's going on inside these complicated instruments in the environment. They studied the young members of the collaboration who really understood how these things work and understood the data channels. They went and they studied key ones among these many data channels to be absolutely sure there was nothing wrong and that this really was just caused by a gravitational wave. And then we announced the discovery. And when we announced the discovery, we, by comparing the signal cleaned up, in some sense this is the cleaned up signal, is the gray oscillation. I'm plotting the stretching of the separation between mirrors up and the squeezing down in units of 10 to the minus 21 for this fractional stretching and squeezing. And the red is from numerical relativity simulations of colliding black holes. And by comparing with simulations for black holes of different sizes, different masses, it was possible then to determine that the source really was from colliding black holes. The initial black holes weighed 29 and 36 times as much as the sun, so that's a total of 65 solar masses. That just means that the gravitational pull was the same as that from a star that weighed 65 times as much as the sun. And the final black hole was 62 solar masses, and so 3 solar masses had been turned into gravitational wave energy. It's as though you had annihilated 3 suns and turned all of their mass into gravitational waves. And that happened in about 1/10 of a second, so the power output, the amount of energy 3 solar masses worth in a unit time, in a time of 1/10 of a second, turned out to be 50 times larger than the power output from all of the stars in the universe put together. 50 universe powers from 2 little black holes colliding for a short time, just 1/10 of a second. But it was the most powerful explosion that we ever had any evidence of except for the Big Bang birth of the universe. And we also, by comparing with the computer simulations, deduced that the distance to the source was 1.3 billion light years. When the result was announced, it made front page headlines in all the major newspapers around the world. But I can just go on my iPhone and I can see, like you can, there were 5 collisions of black holes in that 2-month period. 1 collision of neutron stars. The first collision of neutron stars that was seen 2 years ago was spectacular with electromagnetic emission. This one was not seen electromagnetically, partly perhaps because only 2 of the gravity wave of the 3 gravity wave detectors that we had at the time. By then we had a Virgo gravity wave detector operating, and so we had 3 of them at the time. But with 3 of them operating, you can determine fairly accurately where the source is on the sky. With 1 of them down, you don't get a good location on the sky. So it was harder to see it on the sky, and this thing was quite a bit farther away than the one that was spectacular. There were 2 cases in those 2 months of a black hole swallowing a neutron star whole. Each neutron star is about 30 kilometers across, made of almost pure nuclear matter, mass of about 1.5 times the mass of the sun, and no electromagnetic emission, and reason to believe that the neutron stars were swallowed whole by the black holes. And there were 2 black holes that swallowed something that we're not 100% sure what it was they were swallowed. And they're actually up here. They were both in late September. It's labeled mass gap. The point is that we think that neutron stars don't get heavier than 3 solar masses, and we've never ever seen a black hole, despite huge amounts of astronomical observations, never seen a black hole smaller than 5 solar masses. So that's a mass gap where, and there were 2 signals, one with 100% confidence that it was a object in the mass gap. Here's the 100% confidence. It was an object in the mass gap. And the other 95% confidence. And so this is sort of a breakthrough. There really are compact objects like black holes. They probably are black holes, but nobody had ever seen a black hole this small. And so no technical papers written yet on any of these things. And there's a lot of really exciting science in here. But you can go onto your app and just see the basics of what is likely to come out in these exciting technical papers that are being worked on at the present time. By the late 2030s, 20 years from now, the successors to LIGO and Virgo, which are called Einstein Telescope here in Europe, a large, new, much larger interferometer than what has been operating at the present time, and a similar, much larger interferometer called Cosmic Explorer in North America, will likely see gravitational waves that are maybe 20 times weaker than what is seen today. And that's really impressive. That means if the universe were infinite and flat, you'd be seeing out 20 times farther. You'd be seeing a volume 20 cubed times bigger. 20 times 20 is 400 That's 8,000, is that right? So 8,000 times more frequent events. Instead of one event a week, that's 8,000 events a week. Well, the universe is not flat, and it doesn't extend forever, so it's going to be a little lower than that. But nevertheless, an enormous number of events. Every black hole collision in our universe with masses less than about 100 solar masses is likely going to be seen at that time. A variety of other phenomena on the warped side of the universe. And also by the 2030s, we'll be seeing gravitational waves in 4 different frequency bands. LIGO and Virgo and their successors operate for gravity wave signals that have have wavelengths of oscillation of milliseconds. LISA, a European Space Agency mission that you don't see so well here, let's go up here, consists of 3 spacecraft that track each other with laser beams. And we'll look at gravitational waves with periods of minutes to hours. There's a technique called pulsar timing arrays that I won't talk about at all. But that will see gravitational waves with periods of years to decades. And then a technique called CMB polarization I'll talk about very briefly, seeing gravitational waves with periods of hundreds of millions of years. Of course, that's a little longer than a graduate student lifetime. And so you don't sit there as a graduate student waiting for the signal to oscillate so you can get your thesis on it. Instead, you look at a pattern on the sky of what is called polarization of cosmic microwaves, a pattern that has been produced by gravitational waves from the very early universe, as I'll describe very briefly in a minute. So let me talk about this LISA mission. It's a really exciting mission. I think the science that it's going to do is more exciting than anything that has been done as yet with the ground-based interferometers. I have been hoping it would be launched by 2030, but Bernard says it's such a challenging thing that 2034, which is more likely for when it will be launched. And it's as I say, a European Space Agency mission. It will look for gravitational waves from giant colliding black holes with masses of millions of suns. Also particularly interesting to me is that a small black hole going around a large black hole will obviously create ripples in the shape of space, and those just become gravitational waves that go propagating out. And as was shown by a student of mine, Fintan Ryan, back in the 1990s, the gravitational waves from the small black hole as it's exploring space around the big black hole should carry a full map of the warped space-time of the big black hole encoded in these emitted gravitational waves. And you might ask, well, how can it possibly carry a full map, the warping of time, the warping of space, the dragging of space into motion? If it's just going around and around like that, how's it going to get enough information to make a full map? Well, let me get rid of the warping of space here and just pretend that space is flat around the big black hole. And then let's again look over here where we have more dynamic range on the screen. So the orbit of the small black hole around the big black hole is very complicated. It's nothing like these nice elliptical orbits of the planets around the sun. Why is it complicated? Because gravity is so weird in there. Gravity includes a warping of space, a warping of time, a whirling motion of space around the big black hole, and the gravitational pull. And even the gravitational pull is different than it is here on Earth. It's not an inverse square law, if you know the meaning of that jargon. It's more complicated. And so that gives rise to an orbit that basically samples the entire space around the big black hole and is capable of providing the data for a map. Now, it's a huge challenge with this LISA mission to extract the map from the data, and it's going to be but efforts are underway to develop algorithms to permit that to be done.